Welcome to today's lesson. Let's together look at revision questions on eigenvalues, eigenvectors, and the diagonalization of matrices. We've already looked at these concepts of eigenvalues, eigenvectors, and the diagonalization of matrices. Of course, by now, you already know how to determine, how to find eigenvalues of a matrix and their corresponding eigenvalues. And you also know how to diagonalize a matrix. So today we just want to do more questions so that you get to know how to answer questions from these three concepts. How do you tell if a matrix is diagonalizable? And so again, that is what we'll be looking at today. We already tackled that, but today's lesson will be able to tell how to determine if a matrix is diagonalizable. But just to touch on that, if you're given an n by n matrix, you're given by an n by n matrix, and then we will say that this matrix is diagonalizable. This matrix is diagonalizable. Diagonalizable. If it has n linearly independent eigenvectors. So that is what we'll be looking at to tell if a matrix is diagonalizable. That is the way I in fact be using this. I'll be finding out if this n by n matrix has n linearly independent eigenvectors. And so in that case, then it means you can find matrix, non-singular matrix P, such that P inverse times A gives us D, where D is the diagonal matrix, and the A is the matrix that we've been given. This P, we already discussed it in our previous video, and we said that this P, the diagonalizing matrix P, will be the matrix formed when we write the eigenvectors as columns. So this P is a matrix whose columns are the eigenvectors. So those are some of the things we'll be looking at. But first, let's look at the first question. So we'll go to the first question. The first question is, this is matrix A, find all eigenvalues of A. Then find the maximum set of linearly independent eigenvectors of A. Then is A diagonalizable? D is P inverse times A times P. Now let's first of all do part A. Given this matrix is of determining eigenvalues, and I'll just remind you, the first way was that we take this matrix A and then subtract, since there is a 3 by 3 matrix, I will be a 3 by 3 identity matrix, and lambda is n scalar. Then we will find the determinant of this matrix, what we would then call the characteristic polynomial, and equate it to 0 to solve for lambda. So this is what we used to do. The other way is that if I'm doing then minus lambda square multiplied by the trace of A, multiplied by the trace of A, and then add lambda multiplied by the cofactor of element in position 1, 1, column 1, row 1, column 1, plus the cofactor of the element in column 2, no, row 2, column 2, and then plus the cofactor of the element in row 3, column 3. And then after that, we shall subtract the determinant of A. And I believe this is the easiest of these two methods. and so is the one that I'll be using. I'll be using that. So let's go straight to the answer. I want to do it here, then we create some space. We will do it here. So let me just rewrite my A. My A was 8, 2, -2, and then I had 4, 10, -4, and then finally I had 2, 2, 4. This was my matrix A. Now, so I want to get the characteristic polynomial. It will be lambda cubed minus lambda square multiplied by the A, and then plus lambda multiplied by the cofactor of the element in row 1, column 1, plus the cofactor of the element in row 2, column 2, plus the cofactor of the element in row 3, column 3, then plus the determinant of A. Okay, the trace of A is just the sum of the elements along this main diagonal. So this will be lambda cubed minus lambda square. The sum of these elements, that is 8 plus 10 plus 4. The elements in the leading diagonal, that gives us the trace. Then plus lambda. This is supposed to be minus. This is supposed to be minus. Let me just rectify before we go far. This is supposed to be minus. Supposed to be minus. So you recall that you already have the now. So this is the cofactor of the element in row 1, column 1. This is this element 8. So its cofactor, just delete the row of 8 and the column of 8. So the determinant of the matrix that remains is that cofactor. So the determinant of 10, -4, 2, 4, then plus the cofactor of the element in row 2, column 2. Row 2, this row 2, column 2, this element. So this cofactor of the element in row 2, column 2, I've already said that this is the element 10. So delete the row of 10 and the column of 10. The matrix that remains is 8, -2, and 2, 4. That's the matrix that remains. And then plus the cofactor of the element in row 3, column 3. That element is 4. Row 3, column 3. That element is 4. Delete this row 4. And no, the row of 4 and the column of 4. And you are left with 8, 2. And 4, 10. And then minus the determinant of this matrix. You know, to get the determinant of this matrix, you have very many ways of getting the determinant of matrix. I taught you so many ways. In fact, one of the ways is that you can just remind you, but I'm not doing the determinant. I'm just reminding one of the ways is this, or 3 by 3 matrix. We used this method. 2, 2, 4. And then we added these 2 columns here. Added these 2 columns. And then multiply along this diagonal. And multiply along this diagonal. And then multiply along this diagonal. And add those results. So there is the product here plus the product here plus the product here. Add those. And then again, along this diagonal. You already have answered what you multiply the first three diagonals and add results. So multiply the three other diagonals and add their results separately. Multiply this along these other three diagonals and add the results separately. Now take the last result. Let me call these ones product 4, product 5, and then product 6. And this other one was product 1, product 3. Subtract and sum from the first sum. So we had the first sum where we multiplied along the first three diagonals. That was the first sum. And then we got the sum again along the other three diagonals. So subtract this last sum from the first sum and get your result as 360. So that would be the determinant of this matrix. But we have so many other ways of doing that. So this is 360. The determinant of A is 360. Now, so when you proceed, this would be lambda cubed. Now, what is this? This is 18 plus 4, that is 22. And what is this? So this is lambda into, let's just find the sum here. The determinant here is 40 plus 8, which is 48. The determinant here is that 2 plus 4, which is 36. It just be that 2 plus 4. This is minus, so minus is plus 4. And this is 80 minus 8. 80 minus 8 would be 72. Then minus 6, 360. You can use your calculator to do this. 48 plus 36 plus 72. Let me also use my calculator here. Okay, use your calculator. This would be lambda cubed minus 22 lambda square plus 156 lambda minus 360. This is the characteristic polynomial. Equate this to 0 and solve for lambda. Let me equate it to 0 and solve for lambda. So it gives a cubic equation. And solving a cubic equation, we look at this constant term and write its factors. So the root to this equation is 1, sum of the factors. These are cubic equations, so you have 3 roots. You have 3 solutions. So those solutions should come from among the factors of this 360. So the roots or the factors of 360 are just 1 plus or minus. Let me say plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 5, plus or minus 6, plus or minus 8, plus or minus 9, plus or minus 10, and so on. So we have so many factors. 360 has so many factors. So the 3 roots to this equation must come from these factors. So we use trial to find one factor, and then after finding one factor, we then divide that into this equation to give us a quadratic equation which we then factorize. So just use trial and error. Let's try 1 and see whether 1 is a root here. So if lambda is 1, then we'd have 1 cubed minus 22 times 1 square plus 156 minus 36 And if you use a calculator, you will find that this will not give you 0. That will not give you 0. So that means that 1 is not a root. Yeah, it's not a solution to this equation. Let's try 2. Let's try 2. So when we try 2, then we have 2 cubed, which will be 8. And then minus 22 multiplied by 2 square, which is 4. And then plus 156. And multiplied by 2. Then minus 360. Use your calculator and see what you get. The answer is not 0. The answer is not 0. So try all of these other values. Try all of them until you find one that will give you the answer to be 0. Now, if you try 6, that means you have 6 cubed minus 22 multiplied by 6 square, which is 36, plus 56, 156 multiplied by 6 minus 360, and use your calculator, you will find 0. So that means that 6 is a root to this equation. 6 is a root to this equation. No, not this one. This one. 6 is a root to this equation. It is a solution. So let's now proceed and find the other roots. We don't need to continue by trial and error because this has so many factors that will take us a long time trying all the factors. Since we've already found one of the factors, it's now easy. We try to find the others by long division or by synthetic division. We can use synthetic division, which is easy. Now, so we've now found that one of the factors, one of the roots is lambda 1 is equals to 6. So that lambda minus 6, let me just call it lambda 1, but I need lambda. So that lambda minus 6 is a factor to this, solution, this equation. Now, how do we proceed to find the others? So let me just erase this part so that we can now find the others, the other roots. But we already have that 6 is a root, so that makes our work very easy. So we now use synthetic division to get the other roots. So 6 is a fact. So let's write the coefficients of this equation. We have the coefficient of lambda cubed is 1. The coefficient of lambda squared is negative 22. The coefficient of lambda is 156, which is a positive. And then the other coefficient, this one, a constant, there is 360. So by synthetic division, the first thing I'll do is to bring this one down. And then what I hide out to 6 will be 6. Add negative 22 plus 6 to get negative 16. And then negative 16 times 6 to negative 96. Add this, add positive 156 plus negative, this is negative 96, just add to get 0 then 6. So this thing. And then multiply this 60 times 60 to get 360. And then add again to get 0. So 0 here is the remainder actually, the one we got when we plugged in 6 for lambda. When we plugged 6 right of lambda, I got the remainder of 0. So that means if we were to divide the 6 into this, we would get a quadratic equation, lambda square, 1 lambda square, minus 16 lambda, and then plus 60. Now remember we had the lambda 1 is 6. So we can now factorize this to get lambda minus z minus 10. So just factorize this. You know how to factorize. Let's just factorize it together. So I'm getting lambda minus 6 and lambda minus 10. That's what we get, because if I multiply lambda times lambda, I get lambda square. Lambda times negative 10, I get negative 10 lambda, then negative 6 lambda, which will give us negative 16 lambda, and then 16. Now, so to get lambda 2 and lambda 3, just equate this to 0. And when you equate this to 0, you find that lambda 2 would be 6, and lambda 3 would be 10. And don't forget that we have lambda 1, which was also 6. So we found that our matrix A has 3 eigenvalues. So these are our eigenvalues. These are our eigenvalues. So if this lambda 1 is 6 and lambda 2 is also 6. And so that means this matrix is of this eigenvalue here is of 2 multiplicity. So we have 2 eigenvalues which are the same. And lambda 3 here is 10. Lambda 3 there is 10. So we are done with the first question. The second question wants us to find the eigenvectors. So let's now proceed to that question. I just want to delete this. Just want to delete this one. And let's remember our eigenvalues. Let's now do part B. And let's remember that to get eigenvectors, we take A minus lambda I, and then multiply this by the eigenvector x, and this, let me call it W. Let me call it W, and then equal to 0. I want to let my W here be x, y, z. Of course, the eigenvectors are column vectors. We write it in column form. So I want my W to be that. So our matrix A, let's just remember what our matrix A was. And remember that the first eigenvalue, lambda 1, was 6. So subtract this 6 along the leading diagonal of matrix A. So when you subtract 6 from the leading diagonal, you have 2, negative 2, and then 4, 10, no, 10 minus 6. 10 minus 6, that would be 4. That would be 4, and then negative 4. And then we have 2, then we have a 4 here minus 6 would be negative 2. Multiply this by our W, which is x, y, z, and equal to 0. When this happens, when you can now use Gaussian elimination, and when we use Gaussian elimination, what we then get is 2, negative 2, 0, and this will be 4, negative 4, 0, and this will be 2, negative 2, 0. Now you can multiply this first row by, multiply the first row by 1 out of 2. When you do that, you get 1, negative 1, 0. And these other rows remain the way they are. These other rows just remain the way they are. Now, so having created this one here, we use it to create a 0 in this position and then 0 in this position. That means I need to multiply row 1 by 4 and subtract the result from row 2. So that means I want the new row 2. So it will be the current row 2 minus 4 row 1. I also want a row 3, new row 3. So this will be the current row 3 minus 2 row 1. That's what I want to do. So when I do that, row 1 remains where it is. But then this becomes 0, 0, 0, 0. And this also becomes 0, 0, 0, 0 when you perform this operation. So what do we now have? What we have is x plus y minus z is 0. X plus y minus z is 0. So you then realize that x is a leading variable, but y and z are free variables. So since they are free variables, we let them be parameters. We can say let y be a parameter a and z be a parameter b. So if that happens, then what is x? From here you can see that x will be negative y plus z. So x will be negative y plus z. When you make x the subject of the formula, y will go the other side, becomes negative, and z will also go the other side of equal sign, becomes positive. So x becomes that. So what is our vector? Our vector w, what is it now? So let me just erase some space here, create some space, and now see what my w becomes. Because it's this w that then gives us the eigenvector. It was the eigenvector. It was the eigenvector. So we just want to write it now. We began by letting it be x, y, z. So, but we've now found what x is, what y is, and what z is. So we just need to rewrite it. So that our w therefore becomes, in fact it was x, y, z. But we've just noticed that x is negative a plus b. And y is, this y is a. You can say plus 0b. And then z was in fact b. Z was b. You can say plus 0. And this is the same as if we were to write this separate x and a and b, we would have a here, and a would go into this part as negative 1, 1, 0, and we also have b going here 1, 0, 1. So that means if I'm asked for the eigenvectors corresponding to eigenvalue 6, if I'm asked for the eigenvectors corresponding to eigenvalue 6, then I can see 4 of them. I can see that the first one is negative 1, 1, 0, and I can see that the other one is 1, 0, 1. These are the eigenvectors. Eigenvectors corresponding to lambda 1 is 6. So the first lambda 1, we had lambda 1 is 6, and then we had also lambda 1 is 6, lambda 2 is 6. So that means one could be for this and the other could be for this. So the same 6. The same 6. So one could be for this and the other one for this. So these two eigenvalues have two eigenvectors. We can all see that. So let me just call this first eigenvector as u, and this one as v. Let me just call this one u and v. There's no problem. I'm not even supposed to call them u or v. They are just eigenvectors, but I just want to make my work easier. The next question. Let us now find the eigenvector for lambda is equal to 10. That was another eigenvalue. So let's just erase this. And so when lambda is 10, to equal lambda 3, so let's subtract. We know that we want minus 10i by w and equate this to 0. But w, we want it to be x, y, z. Want w to be x, y, z. So let's just subtract 10 from the leading diagonal of A, and that will give us negative 2, 2, negative 2. Just subtracting 10 from the leading diagonal. You already have matrix A. You already have it, so just subtract 10, and this will be 4. This will give us 0. And this will give us negative 14. And you subtract 10. No, from the leading diagonal, not from the entire row. Just from the leading diagonal. So this remains to be negative 4. And then you have 2, 2, and then with 6. X squared is equals to 0, 0, 0. Now let's use Gaussian elimination. This would be negative 2, 2, negative 2, 0. And this would be 4, 0, negative 4. It's always to ensure that you've done that subtraction clearly. You may forget and subtract from the entire row. Just ensure that you subtract only the leading diagonal from the leading diagonal, so that we have negative 2, 0, and negative 6, and the rest remain the way they are. So that this would be 2, 2, negative 6, this would be 0, 0. Just to do as we did for the first eigenvalue, we did multiply row 1 by 1 out of. This time, let's multiply it by a half, negative a half. Negative a half. I want a positive value here. So when you multiply row 1 by a half, negative a half, what do you get? Get 1 here, negative 1 here, and 1 here, then 0. And these other rows, let them remain the way they are. So row 3 also remains the way it is. This was negative 6, and that is 0. So now, row 1 remains the way it is. But use row 1 to create a 0 here and a 0. That means row 1 times 4 separate from row 2, get a 0 here. This by 4 separate from that, there are 4. And this by 4, and subtract from this, there were negative 8, and a 0. And then now multiply row 1 by 2, and subtract from row 3, to get a 0 at this point. This one by 2, and subtract from this, you have a 4 here. This one by 2, and subtract from this, you have a negative 8 here. Now you can now use row 3 to create a 0 here, and that will give you row 1 remains the way it is. Row 2 remains the way it is. And this one will be 0, 0, 0, 0. So when you use row 2, when you subtract row 2 from row 3. Now, so what do we now have? Let me just write it here. Let me just write it at the top. What I have is x minus y plus z is 0 when I use the first row. And the second row tells me that 4y minus 8z is 0. So then I can say x and y are leading variables, and z is a free variable. So let the free variable be a parameter a. So that if that is the case, then what happens to y? using the second equation, will be 8a. 4y will be 8a, which means that y will be 2a. Y will be 2a. Now let's go to the first equation and find x. X will be y minus z. X will be y minus z. But what is y? 2a. What is z? Z is a. That means that x is also. X is also. So what then follows is for us to write the eigenvector w. So what does it become? We already have x, we already have y, we also have z, so we only need to replace them. Replace x, replace y, then replace z. So w therefore, which was xyz, is x is a, y is 2a, and z is a. In fact, we can factor a out to have 1, 2, 1. So that if I'm asked for the eigenvector corresponding to lambda 3 is 10, is, and give it as 1, 2, 1. That would be the eigenvector. So you then recall from our previous video the use of the words null space, eigenspace, and basis. You then recall from our previous video. But now this is the question. We wanted to find the eigenvectors, and we already have this. We had found an eigenvector u, call it u, another one we call it w, no, v. So let's call this one t. Let's call it t. But as I already said, this is not important. But let's just call it t. Now let's go back to the question and see what the question wanted us to find. Because I remember something like find the maximum set. Let's just go back. Find the eigenvectors. Now these vectors that we found, we already have the eigenvectors. So P would just be the eigenvectors arranged in column form. The first eigenvector, I remember -1, 0, 1. I remember that. No, it was -1. -1, 1, 0. And then the other one was 1, 0, 1. Then the one that we just found was in 1, 2, 1. So this is P. There is no formula in arranging these vectors. You can begin with any. You can even begin with this one, okay? Then followed by any. So long as you arrange those vectors in column form. Now, find P. So what would be D? D would be the diagonal matrix formed. Now, what was the eigenvalue for this eigenvector? This eigenvector, its eigenvalue was it 4? No, it was 6. It was 6. The eigenvalue for this was 6. Then I followed it by 0, 0 in this row. Then 0. This eigenvector, its eigenvalue was 6. So I put it there. And then this eigenvector, its eigenvalue was 10. Then 0, 0. So as I said, in arranging the vectors in P, there's no formula. But once you arrange them in P, remember the order in which they are, and use the same order to arrange their eigenvalues. So if the eigenvector 1 here, its eigenvalue must be the first one. And then this eigenvector here, its eigenvalue must be the second one in this second row. And then the eigenvector here, the third eigenvector here, its eigenvalue must be same. So if I would have begun by this 1, 2, 1, if I would have begun, then this 10 would have come. So that is the only condition. And we've answered that question. That question wanted us to find P and the D. So that you see this D just be the same as P inverse A. At your own time, try and find P inverse, the inverse of this matrix, and see whether this product will give us this. Let's look at another question. Let us now look at this second question. And it's just similar to the one we've already answered. The question is, find all eigenvalues of A. Find a maximum set S of linearly independent eigenvectors A, and then is A diagonalizable? If yes, find P such that D will be given by P inverse times A times P. Now, so straight away we shall find the characteristic polynomial of A, and then equate it to 0 and solve for lambda. So then we just create some space here for our working. Just move this one up a bit. Move it up. I think that is okay. So it's enough space for us. I first of all want to write our matrix A here so that as we determine the characteristic polynomial, we know what we are doing. So a matrix A is 6, negative 2, 2, and then we have 14, negative 10, 2, then we have 12, negative 12, and 4. This is a matrix A. Now, the characteristic polynomial is given by lambda cubed minus lambda square multiplied by the trace of A plus lambda multiplied by the sum of the cofactor 0.11 plus cofactor in position 2, and the cofactor in position 3, then minus the determinant of matrix A. This will be given by lambda cubed minus lambda square. What about the trace? 6 plus minus 10 plus 4. And this is 0. Plus lambda into the cofactor of this position is the matrix that remains when I delete the row of 6 and the column of 6. And that is a negative 10 to negative 12, 4. And then plus the cofactor in the position row 2, column 2, this position will be 6, 2, and then 12, 4. And then plus the cofactor in the position, this position, delete the row and the column, will be 6, negative 2, and this is 14, 10. 14, negative 10. 14, negative 10. Let's just see that we've written the right thing. The cofactor in this position, delete the column and the row, that would be 6, 2, and 12, 4. Let's close the bracket. Then minus the determinant of A. Now, so this has given us 0 actually. So this one is lambda cubed. And the lambda squared times 0 will be 0. Then this one will be lambda into. This is negative 40 minus 24. That is it's 16 negative. That is 16. And this is 24 minus 24, which is 0. And then this was negative 10. Yeah. It was negative 10. Just like it. It was negative 10. So negative 60 minus 28, that gives us negative 32. We know how to get the determinant of a matrix. The determinant of this matrix is negative 128. So this gives us lambda cubed. What is this? Negative 48? Negative 48 lambda plus 128. This is a cubic equation. We can solve it by looking at this constant term. The factors of this constant term, 3 of these factors are roots to this solution, to this equation. Or let me put it to 0. Let me put it to 0. First of all, put it to 0 so that we can solve for lambda. So 3 of the factors of this, the factors of this are just plus or minus 1, plus or minus 2, 3 cannot, so plus or minus 4, 4 can go there, 6 cannot, 5 cannot, so plus or minus 8, etc. So 3 of these are solutions to this equation. Solutions to this equation. So you use trial and see which one accepts to be with you. You use 1 here. For example, you can try 1. So if you try 1, what do you get? You have 1 cubed, which is 1, minus 48 times 1, and then plus 125, 128. And clearly, this is not equal to 0. So 1 is not a root. What about negative 1? Negative 1, you have, so try negative 1. So when you try negative 1, you have negative 1 cubed, which is negative 1, then plus 48, then plus 128. And again, this is not equal to 0. So negative 1 is not a root. What about try 4? Let me try 4. When you try 4, you can also try to proceed and try negative 4, negative 2, then come try 4. But when you try 4, you find that it will be a root because this will give you 4 cubed minus 48 multiplied by 4 plus 128, and this will be 0. So that means that 4 is a root to this equation. First eigenvalue lambda is equal to lambda 1. So lambda 1 is 4. So, and then lambda, we have negative 48. And then we have the constant 128. Bring this one down. 1 times 4, you have 4, then add 4 here. 4 times 4 is 16. Add the base and you get negative 2. Yes, negative 2 times 4, get negative 128. Add this and get minus 0. So the quadratic equation here is lambda square plus 4 lambda minus 22 is equal to 0. So it's this that we again factorize to get the other roots. And so when you factorize this, you get lambda minus 4, then lambda plus 8 is equal to 0, meaning that lambda 2 be putting this to 0. Lambda 2 is 4, and the lambda 3 is negative 8. Lambda 3 is negative 8. So lambda 4, the first lambda 1 was 4, lambda 2 is 4, and lambda 3 is 8. Those are the eigenvalues. So eigenvalues, we found lambda 1 is 4, lambda 2 is 4, and lambda 3 is 8. So what is the question now? The question that we have is the first question, and let's just go back and read the question. Let's go back and read the question. The question is, find the eigenvalues. You've just done that. Find a maximum set of linearly independent eigenvectors, and is A diagonalizable. So let's proceed to part B. Let's get the eigenvectors. So we found that lambda 1 was 4. So when lambda is 4, let's find the eigenvectors. So let W, which is x, y, z, be the eigenvector. Let it be the eigenvector. So what we want to do, therefore, is A minus lambda I followed by W equal to 0. But in this case, our lambda is 4. So in fact, we want A minus 4I followed by W and equal to 0. So what is A? What is A? So A was 622. A was 6, negative 2, 2, 14, negative 10, 2, 12, negative 12. So when lambda is 4, let's subtract that from the leading diagonal. Let's subtract that from the leading diagonal. When you subtract 4 from the leading diagonal, we'll have 2, negative 2, 2, and then 14, negative 14, and then 2, and this will be 12, negative 12, and then 0. Multiply this by x, y, z. There is 0, 0. Use Gaussian elimination. So by Gaussian elimination, we would have 2, negative 2, 2, 0, 14, negative 14, 2, 0, and this is 12, negative 12, 0, 0. Reduce this to echelon form. Okay. Let me just maintain this 2. Or should I make it? Let's just maintain a 2. But you can make it 1 if you want. Now multiply this 2 by 7 and subtract from this second row to get a 0 here. To get a 0 here. I'm multiplying this by 7. This by 7 from this. This by 7 from this. This by 7 is 14. 14 from this, then negative 12. Okay, now multiply by 6, the first row by 6 and subtract third row by 6 from that 0, by 6 from that 0, and by 6, get 12 from that get 12. Of course, the second and third equations are similar. The rows are similar. So let me just, you could ignore one of them, but let me just write this. And that way. So that I used this, added this to that to get a 0. So what I now have is that 2x minus 2y plus 2z is 0. and I also have a negative 12z is 0. The second equation tells me that the second equation tells me that z is 0. But now I discovered that x was a leading variable, z was a leading variable, and y was not a leading variable. So I say let y, which is a free variable, a. So what does the first equation tell me? The first equation tells me that 2x minus 2a plus 0 is 0. In other words, x is a. In other words, x. So what is the w? This was our w. So w therefore, which was xyz, becomes x is a. What was y? Y was a, and z is 0. So in fact, this is the same as a into 1, 1, 0. So the eigenvector therefore is the eigenvector is 1, 1, 0. Or any other vector multiple of this. Any other multiple of that. So let me just create some space. Create some space for I can continue doing my work here. Create some space here. In fact, remember that I've found that when lambda is 4, we had the two eigenvalues, each 4. Lambda 1 was 4, lambda 2 was 4. But we've only found one eigenvector corresponding to lambda is 4. What I mean is we've only found that when lambda is 4, the eigenspace or the null space, let me use the null space. The null space would be 1, 1, 0. This would be the null space. But lambda is equal to 4. There were two of them. It was an eigenvalue of double multiplicity 2. But it has only given us one eigenvector. So let's look at the other one. It was lambda. Lambda was what? Lambda. Then the other eigenvector value was when lambda 3 was negative 8. So we subtract negative 8 from the leading diagonal, and you have a negative 2. So when you subtract negative 8 from 6, so it's 6 minus 8. That would be 14. Let me just correct that. That would be 14. And this other one would be negative 2, then 2. This other one would be 14. And then so just like adding 8 along the leading diagonal. So this would be negative 2, and this would be 2, and this would be 12. Negative 12. Add 8 here. This would be 12. You add 8, the leading diagonal. Multiplied by W, which is XYZ, and equate to 0, 0. And use Gaussian elimination. Use Gaussian elimination. So this would be 14, negative 2, 2, 0. 14, negative 2, 2, 0. You notice that the first equation and the second one are similar, but let's just proceed. Reduce to echelon form. This will be 14, negative 2, 2, 0. Subtract first row from the second row to get 0. 0, 0, 0. Now, this second equation, third equation, third row, so we multiply the first row. 1 to multiply, take the third row, minus 12 over 14, multiplied by row 1. 12 over 14, multiplied by row 1. So row 3 row 3. So we want to get the new row 3. The new row 3, we take the old row 3 minus 12 over 14 over 1. So this by 12 over 14, this is 12, separate from that you have 0. This by 12 out of 14, what do you get? You get negative 24 out of 14. And then subtract it from 12, negative 12 minus negative 2 multiplied by 12 out of 14. So of course this becomes positive, the same as negative 12 plus 24 out of 14. The LCM is 14. Let me just use my calculator to see what that gives. Yes, you can also use your calculator so that we see if we get the same answer. What is my calculator? Okay, I have my calculator. This is negative 12 negative 12 times 14 plus 24. So 144 negative 144 out of 14 to be negative. I don't know whether I've done the right thing. 144 out of 14. I don't know whether I've done the right thing actually. Let me see. Let me try it again. It is negative 12. Of course, this one has given us good. It's negative 12 minus 2. So this is 24 out of 14. So what I did was I took negative 12 multiplied by 14, and to this result I added 24 and I got negative 144. That is correct. Now what about here? I'll take 12 minus 2 multiplied by 12 out of 14. And so this is the same as 12 minus 24 out of 14. So I then take 12 times 24. 12 times 14. Where am I getting? 12 times 14. And then minus 24. That gives me 144 out of 14. Positive. 144 out of 14. And here I have a 0. Okay, so I think I need a bigger space. So let me just erase this part. Erase this part. And I can see that I have the first equation and the second equation. So those are the equations that I want to use. The first equation says that 14x minus 2y plus 2z is 0. And this other one tells me if I was to multiply through by 14, I would have negative 144y plus 144z is 0. In fact, these equations can be, you can factorize. Divide the first one by 2 to get 7x minus y plus z giving us 0. And the other one divided by negative 144 to get y minus z is 0. Now here I can see that only z is a free variable. So let z be a. So that will then mean, the last equation will then mean that y becomes a also. Y is also a. What about the first equation? What does it say about x? It says that x will be a minus a out of 7, which is 0. So we now have a as 0, y as a, z as a. So let's now write the eigenvector. Let me just erase some part of this. I want to erase this part. Erase this. I think I have enough space now. Just want to erase that. So, what is W? W is A, and it was X, Y, Z. It was X, Y, Z. But X is 0, Y is A, and Z is A. This is just the same as A into 0, 1. So that P negative 8, that null space is this 0, 1, 1. 0, 1, 1 is the null space. Now, so the question was, is this A, matrix A, diagonalizable? Is it diagonalizable? And the answer is no. It's not, because I can see that it was a 3 by 3 matrix, but we only have 2 eigenvectors. We needed to have 3 eigenvectors for it to be diagonalizable, because we are dealing with a 3 by 3 matrix. But we only have 2 eigenvectors, so this matrix is not diagonalizable. Therefore, we cannot find a diagonalizing matrix P. We cannot find it. We cannot find a singular matrix P. We cannot find a singular matrix P such that P inverse times D times A times P is D. We cannot find this in a singular matrix. Now let's look at the question if we answered it exhaustively. Oh, this part we've not done it. This part we've not done it. We only got the eigenvectors, and we did not write the set. So the set has to be the set of the vectors. The first vector was what? We found the first eigenvector was 0, 0, no 0, 1, 1. We had 1, 1, 0. And then the other one was 0, 1, 1. So these were the eigenvectors, and therefore this is the set S. So that is the part that we had omitted. But the rest we've already answered it, and that is how we do this question. Let's look at the next one. Now let's look at this question 3, which says that let T be a mapping defined by T maps ABC to A plus half of B minus C, comma, A plus 3 over 2B minus 2C, comma, and then a half of A plus a half of B minus a half of C. Now, so this is the question. Then find all eigenvalues of T, and then find the basis of each eigenspace. And then the other question is T diagonalizable, and if yes, find the basis S that diagonalizes T, and then find the diagonal representation matrix. And let's go straight to the answer. And the way we do this question is just a similar way we've been doing the other questions. Now, so what you do is that you formulate the matrix here. The matrix that I have is, let me just move this. Let me move this one up a bit. Now, so the matrix T will be given by the first element here is A plus a half of B. So that is the coefficient is 1. Then the coefficient of B is a half. The coefficient of C is negative 1. Then we have for this other one, we have the coefficient of A is 1. Then 3 out of 2. Then we have negative 2. Then we have a half. And then another half. And then a negative a half. So this is the matrix T. So what the question is asking is, suppose we're given this matrix T, can you find all the eigenvalues? And then can you find the basis of each eigenspace? And then it too, is this T diagonalizable? So this is the question, and that we shall proceed to find the eigenvalues of this T. And we know how we normally do it. So to do this, the eigenvalues, we already said, and we've seen in the previous examples, that we'll have lambda square, or lambda cubed, minus lambda square multiplied by the trace of T, then plus lambda multiplied by the C11 plus C22 plus C33, and then minus the determinant of T. Now, so this is sum as lambda cubed. This is lambda cubed minus the trace here. We just add 1 plus this 1 plus 3 out of 2 minus a half. Of course, the LCM there is 2, and this will be 2 plus 3 minus 1, which is 2. So this is 2 lambda cubed, lambda square, and then plus a half, lambda plus lambda, followed by. Now, so we are this element. So when you delete the column of that element 1 and the row of this element 1 and the column of element 1, we are left with the matrix 3 out of 2, negative 2, and then a half, and negative a half. So the determinant of this, then plus. Now at this element, delete the row of this element and column of this element, and then you have 1, negative 1, and delete that and that. Have a half and negative a half and negative a half, and then plus. We have this element, delete the column and the row of this element, negative a half, and what you would have would be 1, then a half, this other one will be 1, and then it's 3 out of 2. The determinant of this, and then let's close the bracket, then minus the determinant of A, the determinant of T. Now, so when you do this, let me just create some space here, create some space on the left side. Create my space here on the left side, so that the right side is still there for your reference. Now, so this will give you lambda cubed minus 2 lambda square. Now, this determinant is a quarter. Just multiply this diagonal, which is negative 3 out of 4 minus, but this one will be plus 1, and this other determinant will be 0, and then this other one will be 1, and then you know how to get the determinant of the entire matrix T, which will be a quarter, so negative a quarter. So this, if we simplify, what we get here is lambda cubed minus 2 lambda square. But this is 5 out of 4 lambda. Then minus a quarter. Now, this is the characteristic polynomial. Now, to get lambda, we equate it to 0. And let's multiply through by the denominator, which is 4. And that gives us 4 lambda cubed minus 8 lambda square plus 5 lambda minus 1 is equal to 0. Now, what we have here is a two-tip equation. We want to solve that. So let me just create some space now here. I hope you've already copied this. Just create space here so that we solve this cubic equation from here. Now we have this cubic equation. To solve that, we look at the constant term and then look at the coefficient of lambda cube. So I want to get the roots to this cubic equation. We need to have R out of S, where R will be the factors of the constant term, which are plus or minus 1, and then S will be the factors of the coefficient of lambda cubed, which is plus or minus 1, plus or minus 2, and plus or minus 4. So the factors of this term. So that the roots to this equation is one of the following. I want to divide S into R. And when you divide positive or negative 1 into positive or negative 1, you get positive or negative 1. And when you divide 2 here, you get positive or negative a half. When you divide 4 here, you get positive or negative a quarter. So three of these are solutions to this. So we only need to get one. And after getting one of them, we shall use the method we've been using, the synthetic division, to see whether we can reduce this equation to quadratic equation. Now, when you try, so you'll use trial as we've been doing for the other questions. You try positive or negative 1 and see whether this will give you 0, whether the left side here will give you 0. But you try a half also, positive negative a half. I tried a half, positive a half, and I discovered that positive a half would give me 0. So positive a half is one of so lambda 1 is a half. Then now use synthetic division. Use synthetic division, I have a half there. And then the coefficients here we have 4, we have negative 8, and then we have 5 and negative 1. As we've been doing, let me just remove that, get some space there. So bring this 4 down. 4 times a half will give us 2. On addition of these 2, you have negative 6. Negative 6 times a half, you get negative 3. Add here, you have 2. Then 2 times that, you have positive 1. Add that and have 0. So the quadratic equation, therefore, is 4 lambda square minus 6 lambda plus 2 is the quadratic equation that we want to solve. So we want to solve this quadratic equation to see that we find other roots. Now remember, the first root that we have is the half. So let's solve that quadratic equation. My space is small, so I have to be erasing all the time. So what we have is 4 lambda square minus 6 lambda minus 2 is equals to 0. This is plus 2. Now, so dividing through by 4, then you would have lambda square minus 3 out of 2 lambda plus a half is 0. Now, so this we need to factorize this. You need to factorize this, and when you do this, you get that factorizing this, you have a lambda minus 1, then lambda minus a half is equals to 0 when you factorize this. And you know how to factorize. This. Now, so then what do we have here? What we have here is that, what we see here is that lambda 2 is 1 from here, and from lambda 3 will be a half. So lambda 1 was a half. This lambda 3 is also half. So we have similar eigenvalues, a half. And then the other lambda 1, 2 is 1. So these are the eigenvalues, and that is the answer to question A. So question A, we just write it. Let me delete the whole of this. So for question A, you're saying that the eigenvalues are lambda 1 is a half, lambda 2 is also a half, and lambda 3 is 1. Don't worry about the interchanging of those lambdas. Any kind of lambda 1 and any kind of lambda 2 and so on. So there's no problem. Now, so what are we required now for question 2? Question 2, we are required to find the basis for each eigenspace. So in other words, find the eigenvalues, eigenvectors. Find the eigenvectors. So solution for B. So once when lambda is a half, want to see what will be the eigenvector. So let's subtract this a half from the leading diagonal of T. What do you get when you subtract? There was, what was T? What was T? T was, let's just write what T was. T was a 1, a half, negative 1, 1, 3 out of 2, negative 2, then you have a half, and negative a half. Now, I want to subtract a half from the leading diagonal. So what we want is T minus a half I multiplied by X and equal to 0, where X is the vector, eigenvector X, Y. But let me use W. So where W is the eigenvector X, Y, Z. Now, so when I subtract a half I from this matrix, then I would have a half at this point, and this will remain a half. This will remain negative 1. This will remain 1. So I have 3 out of 2 minus a half, and this is 1. And this is negative 2. And then we have a half. We have a half, and this will be negative 1. So this one is only multiplying by X, Y, Z, and then equating to 0, 0, 0 to find the value of X, Y, and Z. Okay, so from here, as we've been doing before, we go straight to Gaussian elimination. Let's go straight to Gaussian elimination. I remember this is what we want to use for Gaussian elimination. So let me do it to the left side. Because we would not require much space, just a little space for Gaussian elimination. Now for Gaussian elimination, we have a half, negative 1, 1, 1, negative 2, a half, negative 1, 0, 0, 0. So I want to multiply this first row by 2, multiply first row by 2 to get the new first row, and that will give me 1, 1, negative 2, 0. And I want this one to remain the way it is, and this one to remain the way it is. Now use this first row to create a 0 in each of these other rows. So the first row may way it is, multiply by, no, just subtract from row 2 and you have 0, 0, 0. Multiply by a half and subtract from row 3 and you get 0, 0, 0. So that what we have is x plus y minus 2z is 0. Now, so from here we all see that y is a free variable and z is also a free variable, but x is a leading variable. So let's say let y be a and z be b. So for if that is the case, then what is x? X will be negative y plus 2b, no, plus 2z. But y is a, so that is negative a. Z is b. And so what is w there for the eigenvector we are looking for? So it was x, y, z. But x is negative a plus 2b. And y is a and z is b. So let's say a plus 0 and b plus a. In fact, this we can write it this way. We can write it as a into negative 1, 1, 0 and b into 2, 0, 1. So this is W. This is W, the eigenvector. Now, what was the question? The question was find the basis for each eigenspace. So let me just delete this. So it's from this W that we get the answer to that question. So the eigenspace, now the basis corresponding to lambda is a half is suppose set of all vectors, the set of all the eigenvectors corresponding to this eigenvalue, and those eigenvectors, the eigenvector I have there is negative 1, 1, 0 and 2, 0, 1. So this is the basis. From our definition, we say that this is a set of all the eigenvectors corresponding to that specific eigenvalue. And these are the eigenvectors. So this is the basis corresponding to this eigenvalue. Now, so another eigenvalue, that was lambda is equals to 1. So let's just do that. Lambda is equals to 1. So when lambda is equals to 1, let's subtract 1 from the leading diagonal. I can see the matrix here. So when I subtract 1, I will have a 0, and then there is a half, then negative 1, then this is the 1. Subtract 1 from 3 out of 2. That's 3 out of 2 minus 1. The same as 3 minus 2 out of 2, which is a half. And then subtract, okay, this is negative 2. Let's come to the last row, which is a half. A half. Subtract 1 from negative a half. So it is negative a half minus 1. And this is the same as negative 3 out of 2. Negative 3 out of 2. And then multiply this by w. Let's call w to be xyz. Let's call w to be xyz and equal to 0, 0. Using a Gaussian elimination, what we have there, remember that the first non-entry here, non-zero entry should be 1. It should not be 0. The first entry here should not be 0, since we have non-zero entries below it. So we can interchange the first two rows. Interchange the first two rows to have 1, a half, negative 2, then 0, a half, negative 1, and this one remains as a half, negative 3 out of 2, 0, 0, 0, and this goes to, this one remains where it is. Now, this one already has a 0, so we just leave it the way it is. But now multiply this by a half and subtract from row 3. So this by a half, subtract from that, over 0. This by a half, subtract from that, the same as a half minus a quarter. Because even times a half would be a quarter. And the LCM there will be 4, so this is the same as 2 minus 1, which is a quarter. And then we have this by a half, give us negative 1. So what we then have is negative 3 out of 4 plus 1. This is the same as 2, negative 3 plus 2. So this is negative 1 out of 2. Negative 1 out of 2, 0. This was 0. Now, so what do we have now? The first row remains where it is. The second row, we can even multiply it by 2. We can even multiply by 2, or just leave it the way it is. But then multiply it by a half and subtract from this. Because this by a half will be a quarter. Subtract that a quarter from a quarter, we have a 0. So multiply this by a half, you get negative a half. And then this negative a half, subtract from negative a half, and that gives you 0. So from here, what we see the first equation says that x plus a half of y minus 2z is 0. And the second equation says that a half of y minus z is 0. So we just create some space here so that we can see what we have. And these are very easy things. We've been doing them. We did the same in our previous videos. So this is just a repetition of what we already did. Now, from here, we can see that only z is a free variable. Only z is a free variable. Yeah, so let's say let z be a. So if z is a, using this last equation, what would be y? Y will be 2z. Y will be 2z, which is 2a. What about x? This is the first equation. X would be negative y, negative a half of y plus 2z. But y is 2a, so this is negative a. When I multiply this by 2a, negative a. And what about this 2z? This is 2a. So this gives us a. So what about w there, which was xyz? W will be x. X is what? X is a. And y is 2a. And z is a. So this can be rewritten as a into 1 to 1. 1 to 1. And so what is the eigenvalue? No, what is the the basis? So the basis corresponding to this is only 1. So the basis here is a set comprising of the eigenvectors, and the eigenvector there is 1, 2, 1. So the set comprising of this is the basis. Now remember that we said we would denote a basis by this. So the eigenspace is this eigenspace. So this one means the eigenspace of corresponding to lambda is equals to 1. So we can write it this way. This is what it was. The eigenspace would be this way. Set into 1 to 1. So using the same knowledge, you can just write the basis as this. Just write it this way. So this one, whenever I see this, then I remember that this is the eigenvector here. What is inside is the eigenvector when lambda is 1, when the eigenvalue is 1. So this is how I understand this. Now let's look at question C. Question C, we've done a similar question. And question C says, is T diagonalizable? And from our previous knowledge, we say that T would be diagonalizable if, since T is a 3 by 3 matrix, we can get 3 linearly independent eigenvectors. And that's what we got. We got 3 independent, linearly independent eigenvectors. The first eigenvector was what? Get 1, 1, get negative 1, 1, 0. Then we had 2, 0, 1. And then we had 1, 2, 1. So if we were to be asked to find P, this is, in fact, the question is S. So the question is find S that diagonalizes T. Find S that diagonalizes T. So S is this. S is this. So we just arrange the eigenvectors as columns. So this is S. And the question is a diagonal matrix D. So what was the eigenvalue corresponding to this eigenvector? And it was a half. It was a half. So the rest put 0, 0, then 0. And then this one, the eigenvalue corresponding to this eigenvector was also half. Then 0, then you have 0, 0. Then the eigenvector, but the value corresponding to this eigenvector was 1. So this becomes D. And remember what we said, that we can arrange these ones. We just arrange the values, the eigenvalues in D in relation to how we arranged the eigenvector. eigenvectors. So the first eigenvector, its eigenvalue comes first. The second eigenvector, its eigenvalue comes second, and so on. So that's how we do question C. So the answer to question C is that yes, T is diagonalizable because we found that we had 3 linearly independent eigenvectors for a 3 by 3 matrix. Let's look at the next question. Question 4, we are given this matrix, and we have asked to find matrix orthogonal matrix P. Now, I'll underline the word orthogonal because the way you find an orthogonal matrix P is not the same way you've been finding P in the previous examples. In the previous examples, you've been taking the eigenvectors and then arrange them in column form. Then arranging them in column form, the eigenvectors arranged in column form. And that is how we've been finding matrix P. But in the current example that we have here, the word is orthogonal matrix. So what that means is that after finding the eigenvectors, first of all, we would normalize those eigenvectors. You know how to normalize eigenvectors. Is that you take the norm or the length of each vector, length of that vector, and then multiply the reciprocal of this length times the vector. So we shall see how that happens. But we looked at that one before. We looked at that notion before. So the only different thing here is that we shall get the eigenvectors and normalize them first before we form them. So solution. First, we find the characteristic polynomial minus lambda times the trace of A, the trace of A, plus the determinant of A. So this is lambda square minus the trace is 9, so 9 lambda, plus the determinant of this matrix, which is 18 minus 4. 18 minus 4, that gives us 14. Now equate this to 0 and factorize. So when you do that, you get lambda minus 7, lambda minus 2 is equals to 0 when you factorize this, which means that the eigenvalues are 7 and 2. These are the eigenvalues. Now let's get the eigenvector corresponding to 7. Let's subtract 7 from the leading diagonal. You have negative 1, 2, and then 2, negative 4, 0, 0. By 2 and add it to this, there was 0. Multiply this by 2 and add it to this, there was 0, and then 0. So what we then have, if W was xy, what we have here is negative x plus x is a leading variable and y is a free variable. So let y be a. Let y be a. So that means that then x becomes 2a. X becomes 2a. What about w? So w will then be 2a, or a into 2, 1. So the eigenvector, the first eigenvector is 2, 1. That is the first eigenvector. So we will normalize this. We will normalize this later. So let's just find the next eigenvector when lambda is 2. So when lambda is 2, let's subtract 2 from the leading diagonal. We have 4, 2, 2, then this is 1, 0, 0. And this gives us 4, 2, 0. What about here? 0, 0. So what I've just done is that I've multiplied this by half and subtracted the result from this. So this by half from that is a 0. This by half is 1, from that is a 0, and so on. So what we now have is that 4x plus 2y is 0. So let y be n. So that would then mean that that x will be negative a half. Negative a half of n. Negative a half of, because this one further will be negative 2 divided by 4. So that w, the new w, corresponding to lambda is equals to 2 is a into negative a half, and this is 1. Or we can say that is negative 1, 2. When I multiply this by 2, I multiply this by 2, I have negative 1, 2. So this is the other eigenvector. So let me just write what I have. Let me write what I have. What I have is that when the eigenvalue was 7, we found the eigenvector to be 2, 1. Found the eigenvector to be 2, 1. So this is the basis. And when lambda was 2, we found the eigenvector to be 1, 2, negative 1, 2. Now, so we have the eigenvector, this eigenvector and that eigenvector. Let's normalize the eigenvectors. Normalize 2, 1. So normalize 2, 1, first of all, get the length. First, get the length of 2, 1. So length of 2, 1 of this vector is 2 square, which is 4, plus 1 square, which is 1, the square root of that, which is root 5. So that normalized vector there, 2, 1. So let me call this 2, 1 as u. Let me call it u. Let me call it u. U to be 2, 1. So the normalized u will be u with a cap. And I want to say it will be this u times 1 over the length of u. And the length of u is what we found to be 1 over. So this then gives us 2 over the length, and which is that. And then this 1 over the length, 1 over the length. So this is our normalized vector. Now let's also normalize, let me call this, let me call v. Let me call this vector eigenvector v. So I want to normalize v, so I get first of all the length of v. So the length of v will be negative 1 square, which is 1, and then 2 square, which is 4. And so these are again with the length root 5. So that the normalized v, and so that will be negative 1 out of root 5 and 2 out of root 5. So that is our normalized vectors. These are our normalized vectors. So the P, the orthogonal matrix, and you remember the word orthogonal matrix for it. So P will now be the matrix formed by these normalized eigenvectors arranged as column in column form. So this will be 2 out of root 5, then 1 out of root 5. And this other one was negative 1 out of root 5, and this is 2 out of root 5. So this is the normalized vector. What the word normalized? No, this is the orthogonal matrix P. Orthogonal matrix P. And the word orthogonal here means that if I were to take this matrix, the transpose of this matrix P would be the same as the inverse of the matrix P. As an orthogonal matrix. The matrix orthogonal is the transpose of that matrix is the same as the inverse of that matrix. Now, so what is D? What is D? This normalized eigenvector was the eigenvector corresponding to lambda is equal to 7. And this normalized eigenvector was the eigenvector corresponding to lambda is equal to 2. Lambda is equal to 2. So this might be. This might be. But the only trick was at this point that P was to be orthogonal. So we are first of all to normalize the eigenvectors before we arrange them in column form to form P. Now, so if you wanted to find the inverse of this matrix, you would use the same way, or since it's an orthogonal matrix, the transpose of this would just be the same as the inverse. So you know the transpose, you arrange this row as a column, and then this row as the second column. So that would be P inverse. But the question wanted us to find P and D, and that's what we just done. Now let's look at this question 5, and you notice that I've set this question 5 to be similar to question 4. And I want to emphasize on how to get orthogonal matrix. As we've done in question 4, you remember that we want first of all to get, when it comes to this part B, we'll get the eigenvectors and then normalize them. And arrange the normalized eigenvectors as columns to form. So that is the only thing that I want to emphasize. Now, so let's go straight to the solution. Now, I'll avoid much details because you already know the details. But first of all, we need to get the characteristic polynomial. And the characteristic polynomial here will be given by lambda cubed minus 2 minus lambda squared multiplied by the trace of A multiplied by the trace of A plus lambda multiplied by cofactor 1, 1 plus the cofactor in position 2, 2 plus the cofactor in the position 3, 3. Then minus the determinant of matrix A. Now, so this, you know how to do it. And when I did this, I found that I would have lambda cubed minus, so let me just add 4 minus 4 plus 4, and that will give me 4 lambda square. And then this will give me, just a minute, and then I would have plus lambda into, now I got this determinants as a negative 4 plus 12, then plus 4, or minus 4. I got it as minus 4. And then this other determinant, I got it as 0. So this gives me lambda cube minus 4 lambda square. And when I do this, I get 4 lambda is equals to 0. So this is the characteristic polynomial. I want to solve it for characteristic equation because I was saying it equals to 0. So let me solve it for lambda. That means I would factorize, and I get lambda square minus 4 lambda plus 4 is equals to 0. So that means I can also factorize this. And when I factorize this, I would have lambda into lambda minus 2 square is equals to 0. So this then means that this lambda is 0, lambda 1 is 0, and then lambda 2 is 2, and lambda 3 is also 2. So this is what I get as the characteristic, the eigenvalues. These are the eigenvalues, 3 eigenvalues. Let me see, let me now find the eigenvectors. So when lambda 1 is 0, let me subtract 0 from the leading diagonal, and I would have 0. No, subtracting 0 from the leading diagonal. I would have 4. 4 was our matrix. was 4, then there was -6, and then there was 2, and then this is 2, subtract 4 from this, 0 from that, and then I have this, and then I have 2, and -6, and 4, 0, 0. And so when I reduce this, of course, I'm multiplying that by W, and my W is XYZ. So when I reduce this, I will have, you can just multiply this by, it. Let me just maintain the 4, 4, 6, 2, 0. Multiply this by a half, the first equation by a half, and subtract from the second equation. So, no, this first row by a half and subtract from the second row. So this by a half is 2, from that is 0. This by a half is -3. From this I have -1. This by a half is 1. From this I have 1, then 0. Again, the same thing by a half, and subtract from row 3, I'll get 0. Then this by a half is -3, and subtract it from -6, you get -3. And then this by a half, you get 1, subtract from that, you have 0. So this will go to 4, -6, 2, 0. And now I want to use this here, create a 0 here, so that the first row, the second row remains where it is. And then I'll be multiplying row 2 by 3 and adding to row 3. So multiply row 2 by 3, add it to row 3, hit adding, subtract. So this by 3 would be -3. -3 add this. No, -3 subtract from -3. This is 0. Now this by 3 will be 3. Subtract from 3 about 0. So this is what we now have. What we have is that 4x minus 6y plus 2z is 0, and this other one is -y plus z is 0. We have these two equations from which we can see clearly that z is a free variable. So we let it to be n. Let it to be n. So let me just create something. So I've just said that z is free, the variable, so let z be n. So what does the second equation tell us? The second equation then tells us that y would be also n. Y will also be n, because negative y will be -z. Now what about x? So then we have the first equation telling us that 4x will be 6y minus 2z. But then for x will be what? 6y, y is a, minus 2z, z is a. So that x will be 3 out of 2a. When you divide through by 4, this will be 3 out of 2, and this will be a quarter, no half. The half of it. What was this? I didn't even need this. I would just have said for and then say that x becomes a. Because it does the same thing I get here. Because this would be what? 2 into this would be 2. So that is just 2. That is just a. So I'll just have said that So X is A. So what about W? The eigenvalue. Let me just say there. Okay, so W is X is A and Y is A and Z is A. So these of them as A into 1, 1. So that the eigenvector corresponding to lambda is equals to lambda is equals to 0 is 1, 1, 1. Now, so let's find the eigenvector corresponding to the other lambda. The other lambda was 2, and it was of multiplicity, double multiplicity. So let's now find when lambda is 2. Just subtract 2 from the leading diagonal, and you have 2 there. There is 6. This was 2, I think. That was 2. Subtract 2 from the leading diagonal only, and this would be 2, negative 6 here. And this would be 2, and then this is 2, negative 6 here. And this would be what? 2, 0, 0, 0. And reduce this. You remember there is x, y, z multiplied by x, y, z, and then equals to 0, 0, 0. So we're just using Gaussian elimination straight away because I know that the other steps you're familiar with them. So this will be 2, negative 6, 2, 0. And of course, you can see that this should be zeros. And this should be zeros. From here, what we now see is x minus 6y plus z. X and y and z are free variables. So let y be A and let z be B. So that x would be 3a. When I take the other side, 6 divided by 2, and then this will be negative b. Negative b. So what about w? W will be 3a minus b. And y here is a plus 0, and b here, no, z here is b plus 0. In fact, what we are saying here is a into 3, 1, 0 plus b into what? Negative 1, 0, 1. Negative 1, 0, 1. Negative 1, 0, 1. So E2, we've said, would be 3, 1, 0 and negative 1, 0. So that is E2. Those are the eigenvectors. These are the eigenvectors when lambda is 2. What is it? This is 0. From this. The other one is 3, 1, 2. Now, so what is the question? We had, when E was 0, we found the eigenvector was 1, 1, 1. This was the eigenvector. So now we want to answer the last question B. We already have the eigenvectors. That is part of question B. But what remains is to find the orthogonal matrix. That means we first of all find the normalized eigenvectors. Normalized eigenvectors. Let's normalize the first one when lambda is 0. So let me call it U. Let me just, it's already, let me just call it. Or let me call it U. Let me call it. So that the normalized U will be 1, 1, 1 multiplied by the length of this, which is 1 over the length, which is root 3, So this is 1 over root 3, 1 over root 3, 1 over root 3. Okay, now let's now normalize this. I want to call it B. I want to call it normalized B. The length here I can see it's 9 square, 3 square plus 1 square. It's root 10. So 3 out of root 10, 1 out of root 10, and 0. And then let me call this one, let me call it T, or yeah, call it T. So the normalized T, now the length here is root 2. So root 2 not get length. So I have negative 1 out of root 2, then 0, then 1 out of 2. So what is P? What is P? P, therefore, we just arrange these vectors as column. 1 out of root 3, 1 out of root 3. And then let me get enough space. Let me get enough space. I want to write it above. To write it. So P, therefore, is 1 out of root 3, 1 out of root 3, 1 out of root 3. That's the first column. The second column is 3 out of root 10, 3 out of root 10, 3 out of root 10. And the last one is the negative 1 out of root 2, 0, 1 out of root 2. So this is the orthogonal matrix P, which diagonalizes matrix P here. I remember, I think in this question I was using matrix tensor in one of the answers, but it's B not. Now, so the question is, find the diagonal matrix of P. So D, we just arrange these columns. We arrange the eigenvalues of these eigenvectors in the order in which they appear. So D will be this eigenvector was corresponding to eigenvalue 0. I think so. Eigenvalue 0. So the rest will be 0, 0. And then this other eigenvector was corresponding to lambda is 2. And this other one was corresponding to lambda is 2. So this is the but you can arrange and have them. You can even arrange P and begin with this, begin with this, and follow this, then end with this. So that and then 0, 0 comes to the bottom. Can you see how to arrange? So what about P inverse? P inverse will just be the transpose of this matrix, the transpose of P, because P is orthogonal. Now let's look at this question 6. Question 6 says P is a 2 by 2 matrix such that the null space or the basis corresponding to lambda is 2. See, this 2 is the eigenvalue, and this 5 is the eigenvalue. So then the eigenvector is that, and the eigenvector here is that. So they're just telling us that when eigenvalue is 2, the corresponding vector is 2, 1. And when the eigenvalue is 5, the corresponding eigenvector is 1, 1. And the question is find P, find this matrix P. So for us to find this matrix P, we must remember that P is given as P D P inverse, where P here is a matrix formed by arranging these eigenvectors in column form as columns. So this would be our P. This would be our P. What about our D? Our D, so this eigenvector here, its eigenvalue is 2. And this eigenvector here, its eigenvalue is 5. So this is a P. So you only need to get P inverse. You only need to get P inverse. And P inverse would be 1 over the determinant of P. The determinant of P here is 2 minus 1, which is 1. Then times the adjoint of P, where we just reverse this getting diagonal and change the signs of this other diagonal. So this is our P inverse. 1, that is 1, that is 1, 2. So the question then is, what is P? So just multiply this by that, by this, and solve it. Let me create some space here. So this means that P is P D P inverse, but P is 2, 1, 1, 1. D is 2, 0, 0, 5. And P inverse is 1, negative 1, negative 1, 2. When you do that, you can multiply that. So I was getting negative 1, negative 3, 6, 6, 8. Now let's look at question B. Now from above, we've seen that matrix B is given by P D P inverse. Now, so the power on B here is 1, so that means D is raised to power 1. But now when we get B raised to 6, we would have P B raised to 6, then P inverse. That's how we shall get B raised to 6. Now we've already learned how to raise the matrices to powers in our previous video. Now, so in this example 6, we found from above that matrix P is 2, 1, 1, 1. We've also found P inverse to be 1, negative 1, negative 1, 2. And we found D to be 2, 5, 2, 0, 0, 5. This one was given in our question, in the question. And therefore, B raised to 6 would be P times D raised to 5, now raised to 6. D raised to 6 times P inverse. And this is the same as P is 2, 1, 1, 1, and then D is 2, 0, 0, 5. Now, so we raise this 2 to 6, and then this 5 to 6. Because we know that is 0 raised to 6, we just 0. So we just raise the elements along the diagonal, and then multiply by P inverse, which is 1, negative 1, negative 1, 2. So if this happens, then you get negative 15,497. This is 97. And then that 1,122. And at this point, we would have negative 1561, and then here we would have 31186. So this is b raised to 6. But what the question wants is b plus b raised to 6. But question A has already given us b. We found b to be negative 1, 6, and then 3, negative 8. No, this is negative 3, then this is 8. So when I add this to b raised to 6, which I have above, b raised to 6 is negative 15,497, and this is negative 15,561. That 122, and that 186. This sum would then give me what the question wants, which is negative 15,498, and that 128, and this part I would have negative 15,564, and this other element here is that 194. So this is what the question wants. And what was very important is to know how to get b raised to 6. But we had done this earlier in our previous video. So we had already said that if b is raised to any number here, supposing b was raised to n, then we would have p times d raised to n times p inverse. So that's how we define a matrix raised number. And you remember in our previous video, when we found the square root of p, and we said it would just be the same as p times the square root of d times p inverse. So that's how we do this question 6. Let's look at the next question. Now, so this question 6 is just question 7 here is similar to the previous question. We are given a symmetric matrix here. You know what a symmetric matrix is? That the transpose of b is the same as b. That's what we mean by symmetric matrix. So if you get the transpose of b the same as b, so b is the same as b transpose. That's what we mean by symmetric matrix. Just to remind those who may not be remembered. Now, so the question here to me is the word orthogonal. That will find the eigenvalues, eigenvectors, and then normalize the eigenvectors, and write the normalized eigenvectors as the column of p, columns of p. That's what we want. And then also tell us what p is. So very first, let's find the characteristic polynomial lambda cubed. You know how to do that? Lambda cubed minus the trace multiplied by lambda square is a trace of p, and then plus the cofactors multiplied by lambda, with the cofactor in the position 1, 1, the cofactor in the position 2, and the cofactor in the position 3, 3. Then minus the determinant of p. Now, when you do that, what you then get is lambda cubed got plus 5 lambda square. You do it at your own time and see that you get the same thing. This is 42 lambda, then minus 144. Equal to 0, and solve for lambda. So I did factorize this. and found that when you factorize this fact, you discover that lambda 1 would be -3, and then lambda 2 would be 6, and then lambda 3 would be 8. So if you don't know how to get these characteristics, these eigenvalues, you can always ask on the link. I always show you how I got them, but I'm hoping that the previous examples that I've shown you would help you to do this. Now, so then what did I find the eigenvectors to be? And I found that the eigenvector, when eigenvalue is -3, I found it to be 1, 1. I found this to be 1, 1, 1. Then I found the eigenvector when lambda is 6 to be -5, 4, 1. And then when lambda is 8, I found the eigenvector to be possibly -8. Possibly, just write it properly. Supposed to be -8 out of 8. Lambda 3 is supposed to be -8. So just confirm and so you get. And so that one, when lambda is -8, I found it to be -1, -2, and then 3. -1, -2, and then 3. Yeah, that's what I found. These were the eigenvectors, and these are the eigenvalues. Then I now normalize this and arrange them in column form. Just normalize and arrange them in column form. And I know you know how to do that. So when I do that, and then I found that P would be, I want to arrange, P would be -5 out of root 42, 4 out of root 2, 42, and 3 out of root 42. Then this other one, this is not correct, this is 1. This one, remember it was -5, 4, 1. -5, 4, 1. This other one will be 1 out of root 3, 1 out of root 3, and then 1 out of root 3. And then this, the last one will be 1 out of root 14, and then 2 out of root 14, and then -3 out of 14. Because this was 1, 2, -3. Now, what about D? Its eigenvalue was what? Was 6. Then 0, 0, 0. The eigenvalue for this eigenvector was -3. And then the last eigenvalue was -8. So this is the P. The question does not want us to find P transpose. But it's easy. If you want, you can just get P transpose from this. Make this first column, this first row to be the first column, second row to be the second column, third row to be the third column. So now let's look at the next question. I'm now moving faster because you already have the concepts. You've done similar questions before. Look at this question. We've done a similar question. We are given a 3 by 3 matrix, and we're told that the first eigenvalue is 0, and its corresponding eigenvector is 1, 1. The second eigenvalue is 1, and there are 2 of them, and they have 2 eigenvectors. And the first eigenvector is that, the second eigenvector is that. Compute the determinant of a raised to 4 plus a. So for you to get raised to 4, first of all, you must get what a is. And a, as you've seen previously, will be given by p times d times p inverse. This is a. But what is p? P, just arrange the vectors. Just arrange the vectors. Just arrange the vectors as columns of p. 1, 0, 1. What about d? This eigenvector had 0 as eigenvalue. And this other one, I can even rearrange the way we had talked before and begin with this one. And begin with this and then end with that. Just rearrange this. I want zeros to be at the top. Rearrange and begin with 1, 2, 0. 1, 0, 1, and then 1, 1, 1, because I know that this will be 0. And so that d, now, this eigenvector has the eigenvalue 1. This eigenvector has the eigenvalue 1. And this eigenvector has eigenvalue 0. So this is a d. Now we can find p inverse. You can find p inverse. You know how to get the inverse of a matrix. And p inverse, I was getting 1, 0, negative 1, then 2, negative 1, negative 1, then negative 2, 1, 2. If you don't know how to get the inverse of a 2x3 matrix or higher order matrices, then you can check one of my previous videos on how to do the same. Now, so what is there? What is there? A is P, D, P inverse. Just arrange them and multiply. We'll get A to be 3, 1, 2, and then 2, 0, 2, and then 2, negative 1. This is A. When you multiply P times D times P inverse in that order, this will be A. So what is A inverse? What is A raised to 4? Now, what is A raised to 4? So from the previous knowledge, A raised to 4 will be given by matrix P times B raised to 4 times P inverse. What is P? We found P in our previous, we found it to be rows P. Of course, we found P by arranging these eigenvectors as column, and our P was 1, 2, 0, and then 1, 0, 1, and this was 1, 1, 1. And then D, we've just found D. We were given the eigenvalues. And so we began with 1, 2, 0. 1, 2, 0, the eigenvalue is 1, 0, 0. And then we followed by 1, 0, 1. 1, 0, 1, the eigenvalue was also 1. And then we followed it by 1, 1, 1, whose eigenvalue was 0. Now, since we are taking D raised to 4, we just raise the numbers along this diagonal to 4. so that we have 1 raised to 4, 0, 0. For 1 raised to 4, just be 1. And again, this 1 raised to 4, just be 1, and so on. And then followed by P inverse, which we found to be 1, 2, negative 2, and then 0, negative 1, 1, and then negative 1, negative 1, 2. So this gives you P inverse, no, A raised to 4. When you do this, when you multiply this matrix by that, and then multiply the result by the next matrix, you get this answer to be 3, 2, 2, negative 1, 0, negative 1, and then 2, negative 2. This is also negative 2 here, and then negative. So this is A raised to 4. But what the question wants is A raised to 4 plus A. So we take this A raised to 4 plus A raised to 4 plus A. And when I did this, when you do this, when you just add these two matrices, it's very easy to add matrices. We all know how to do that. You get 6, 4, 4, and then you get negative 2, 0, negative 2. Then at this point, you have negative 4, negative 4, negative 2. But what the question wants, of course, is the determinant of this sum. And it wants the determinant actually. Wants the determinant. But the sum will be the sum of A raised to 4 plus A is the same as 6, negative 2, 4, and then 4, 0, negative 4, and then 4, negative 2, negative 2. But now the determinant is 0. That's all the question wants. So at your own time, you can do it slowly and see how to get that. But I've already shown you what you need to do. I've already shown you what you need to do.